Good morning, students. My apologies if it is an afternoon session. Haha. I hope my joke helped you overcome post-lunch sleep. The experiment in our hand today is magnetic field along a current-carrying circular coil. I believe you have learned Biot-Savarth law in your 12th class. A line segment of current will produce magnetic field around it. The magnitude of magnetic field at a point away from current is proportional to the magnitude of current and inversely proportional to the distance between the point and current segment. In this experiment, we will slightly move from there to a circular coil carrying current and measure magnetic field at the center of the coil and away from the coil, on the axis of the coil. This is also covered in your 12th class syllabus. Before moving into the details of experiment and applications based on magnetic field production at a distance using current-carrying coil, let us have a feel for magnetic field strengths of different instruments we use. Earth magnetic field is around 0.3 to 0.6 Gauss depending on which place on Earth you are measuring. It is 0.38 Gauss here, in our current location. Compared to that, the fridge magnets we use at home are about 250 times in magnitude, that is about 100 Gauss. Your earphones use magnetic fields of about 200 Gauss and loudspeakers can be anywhere between 8,000 to 20,000 Gauss. However, in sound systems, the high magnetic field is confined to a very narrow region between magnet and voice coil. On the other hand, an MRI machine uses 5,000 to 70,000 typically, and much beyond in some special cases. In the case of MRIs, the field is much extended in space, and for such large magnetic field strengths, ferromagnetic materials like your keychains, coins, watches, etc. get pulled very strongly to the extent of injuries. ATM cards and ID card containing magnetic memory get erased. For safety, all MRI rooms have a protocol to check for all objects a patient have before letting him come near machine. The derivation to arrive at a formula to measure strength is there in your 12th class. We are going to use multiple rounds of coil bound close to each other, and the choice of current is such that the generated magnetic field will be comparable to Earth magnetic field values. I am not going to tell you exact numbers. That is your experiment here to measure. The wires carrying currents to coil are tied together so that the net current and magnetic field from that is zero. Only the current in circular coils produce magnetic field. If the current coil is wound to extended length in a straight tube, it is called a solenoid. Please do remember there are more applications for solenoid-generated magnetic field than a short loop like our experiment. However, our experiment demonstrates what is necessary for such applications. If the coil is wounded around a circular tube, it is called a toroid, and the magnetic field lines inside the toroid are confined within the tube, and such arrangement will have advanced application in particle accelerators where elementary charges particles need to be confined. That includes Large Hadron Collider at CERN, which is a 21 km ring underground at a depth of 50 to 175 meters below ground and maintained at ultra-high vacuum. This is the experimental setup we are going to use in our laboratory. The length of the long horizontal stand will have a loop of coil at the center, and the stand and magnetic field is produced along the stand. We will keep the stand perpendicular to the Earth's magnetic field direction, so that the coil-generated field will be perpendicular to it. The magnetic compass rotates from Earth's magnetic field direction to coil-generated field direction, with angle of rotation proportional to the generated magnetic field value. The magnitude of coil-generated magnetic field at a point is simply tan theta times the Earth magnetic field. Our experiment is as simple as that. Let us look into the applications now. This is an MRI machine. Looks great, isn't it? Let us slice it and diagnose the interior. What is inside is basically a current-carrying coil, a solenoid to be precise. However, the magnitude of current is very high and we need superconducting coils. Despite the high magnetic values, you don't feel a thing inside the machine unless you swallow ferromagnetic materials. The coin may rupture your gut and skin to come out in such high magnetic fields. Of course, I am joking about such remote possibility a person swallowing a metal, but I'm not joking about what happens if he or she swallows it. It is dangerous. Nevertheless, what if we use such idea of converting magnetic field strength into mechanical energy? That is where the applications of valves, locks and flow control units come into play. They are there for very long time in a variety of machines used in homes and industry. You just need to keep magnetic material to hinder the flow of liquid, and you can control it with switching a solenoid on and off, thereby moving blocker in and out of the flow. Apart from blocking completely, if we can optimize the field values to opposing forces, we can partially close the valves, thereby fuel flow can be controlled with our accelerators. We can also make our gear shifts smoother, etc. Similarly, the door locks can be controlled through digital keys, which in turn are connected to current switching. All these applications are closely related, and it is only our ingenuity how we can put them in process. A doorbell also uses a solenoid to activate chime mechanism. Similarly, a wireless mobile charger uses two coils, similar, but not exactly the one we spoke so far. One will generate magnetic field when current flows, and the other uses that magnetic field to induce current, thereby charging a mobile battery. One should remember the efficiency of power transfer is less in this process, and we see more heat than in a wired charging. What if we deliberately increase the heat generation at the receiving material and use it to cook? We call that an induction stove, and we use a material which produces eddy currents to convert the magnetic field to heat via current in the material. However, to produce eddy currents, we need an alternating current unlike previous applications. I hope you got a feel for the experiment and its application. Please start your experiment. Take good care of your instruments and they take care of your results. Happy experimenting.